So hello, good evening everyone. I'm Associate Professor Naomi Frangos, Coordinator of Lectures and Exhibitions, and on behalf of Dean Maria Perbolini and everyone at the School of Architecture and Design at NYIT, I'd like to welcome you to our opening lecture for this spring in continuation of our series about fast-forward thinkers and makers. While our fall sessions focused on making praxis, exploring the agency of practice by which layers of transdisciplinary knowledge are enacted, activated, and revealed through making, our spring follows in proximity with making mediums. Mediums implicates a broad range of working methods, both material and abstract, speculating on the agency of mediums, both as physical matter and modality of communication, with the power to generate sensory experience, but also convey it. It also considers atmospheres, ephemerality, animation, changing environments, seasons, temporal conditions of architecture. Tonight, our guest speaker is Jenny Sabin, Weisenberger Professor in Architecture and Director of Sabin Lab, Department of Architecture at Cornell University, and Principal of Jenny Sabin Studio. The lecture will be followed by a discussion moderated by our school's Associate Dean Professor Tom Verabes, and our upcoming lectures and events are also posted on our website and social media. Our March 27th, Diana Agrest, Professor from Cooper Union, April 10th, Gundula Prosh, Professor in Landscape Architecture at University of Washington. February 27th, a roundtable panel on unprogramming computational processes, moderated by NYIT Associate Professor Marcella Del Signor. And in April 17th, we have a symposium entitled Automation by Design, organized by NYIT Digital Technologies and Fabrication Director Dustin White and visiting Professor Pavlina Vardulaki, co-founder of Design Morphine. So I've been inspired by Jenny's work for some time now. I recently had the opportunity to meet her during a Design Communication Association conference at Cornell last fall, where she was keynote speaker. I visited her lab and witnessed the integration of hand and machine busily at work in preparation of her show, Luster. Jenny was invited to collaborate with Art Production Fund and House of Peroni to create an adaptable installation for various settings in 4 different cities. With kind invitation, I attended the opening and was inspired to write a short article called Knit Nature that was published in the Architect's newspaper. Here's a few excerpts where I liken her work to Wolfgang von Goethe's scientific understanding of dynamic archetypes in his treatise on botany focused on transformation and evolution rather than fixed forms and species. Rather than imitating nature and scaling up data or images found in nature, her canopy structure is created through an understanding of morphology relationships between generative and computational design. Variable instances of growth are staged, played out in a luminous performance of surfaces rising and falling as if inverted stalagmites captured in formation. Like Goethe's sensual dynamic archetype, Sabin's coevolutional structure and materiality is animated by an opening and closing cellular system, distressed and stretched into unique familiar shapes. The systematized fabric sprouts a second life with striation patterns coming alive in alternating light and color transformations where one by one photoluminescent knit fiber knits are activated to release light. Jenny Sabin's sensory and material choreographies create this haptic desire. They set up responsive behaviors between naturally swaying textured archetype and the human body, finding semblance in Anne Hamilton's topography of irregular patterns of variegated horsehair fibers, or more to her gigantic hung textiles in Habitus's twirling perpetual motion. Moving beyond the organics, Sabin's ethereal fabric surfaces dislodge the static experience to engage the body as perceptual devices, a testimony to human curiosity, sensory indulgence, and bodily silhouettes. Moving away from masculine formulaic Cartesian space that relies on mathematical principles, Sabin refers to more feminine systematic network assemblies that don't follow a rigid order. The porous, soft, intimate nature of knit engages the visitor's desire to touch and peer into. Non-programmed openings generate organic distribution of holes, giving the cone structures a degree of autonomy. Her approach blurs the boundary between the objectivity of science and subjectivity of our perception. A bit about Jenny. Jenny is an architectural designer whose work is at the forefront of a new direction for 21st century architectural practice, one that investigates the intersections of architecture and science and applies insights and theories from biology and mathematics to the design of material structures. She is Arthur L. and Isabel B. Weisenberg Professor at Cornell. She established a new advanced research degree in matter design computation. She's also principal of Jenny Sabin Studio, an experimental architectural design studio based in Ithaca, and director of Sabin Lab at Cornell AAP. She holds degrees in ceramics and interdisciplinary visual art from the University of Washington and a Master of Architecture from University of Pennsylvania. She was awarded a Pew Fellowship in the Arts in 2010 and was named a USA Knight Fellow in Architecture. In 2014, she was awarded the prestigious Architectural Lead Prize. Her work has been exhibited internationally, including at the Frac Center, Cooper Hewitt Design Triennial, and most recently as part of the Imprimer Le Monde at Le Pompidou. She earned her master's with honors at UPenn, and she also, when she gained her bachelor's, had a minor in art history at Washington. She has won numerous awards, notably she was the winner of MoMA's PS1 Young Architects Program in 2017, Innovator Award of Architectural Record 2016 Women in Architecture Awards, and Ivy Innovator in Design National Award recognizing and supporting the next generation of leading minds in technology, film, and design. She was also Acadia's Excellence in Digital Practice Award and New York City Architectural League Prize for Young Architects. She's also received several fellowships, scholarships, and other awards. For over a decade, she has participated in international conferences, symposia, exhibitions, such as Session Chair by Invitation at Fabricate 2017 conference in Stuttgart, Germany, and Living Architectural System Symposium in Waterloo, Canada in 2016. Also co-chair Adaptive Architecture and Programmable Matter, Next Generation Building Skins and Systems from Nano to Micro, Materials Research Society, the first symposium at the annual exhibition and meeting chaired by architects in 2014. She's highly active with memberships and forging academic and design excellence, such as Arc and Tex, board member at Acadia, sits on editorial boards for international journals, namely 3D Printing and Renewable and Sustainable Energy. Together with Peter Lloyd-Jones, a cell and molecular biologist, Jenny published the book Lab Studio, Design Research, Architecture, and Biology that is on sale here after the lecture. So tonight, Jenny's talk, Matter Design Computation, Biosynthesis and New Paradigms of Making, will present her ongoing transdisciplinary research and design spanning across the fields of cell biology, material sciences, physics, fiber science, fashion, electrical and systems engineering, and architecture. Through the visualization and materialization of dynamic and complex data sets, Jenny Sabin has generated a body of speculative and applied design work that aligns craft-based techniques with digital fabrication alongside questions related to the body and information mediation. So without further ado, I ask you to kindly silence your digital devices and please give a warm welcome to our guest, Jenny Sabin.
Wow. Thank you for the wonderful introduction, Naomi. Thank you, everyone, for coming out this evening for my talk. First of all, I want to thank Naomi for the invitation and the New York Institute of Technology, the School of Architecture and Design for this incredible series. I have a lot to share with you, so I will try and keep this within 50 minutes or so that we have a good amount of time for a Q&A and discussion with your Associate Dean, Tom Verbes. So I'm going to address the topic of my lecture through the lens of my transdisciplinary collaborations. And this stems from an interest in developing an alternative material practice in architecture. And this is done through the generative fabrication of nonlinearities, of material and form across disciplinary boundaries. And I'm going to talk about the foundation for the work, talk about some key collaborators that have inspired me for the last 15 years, as well as some new collaborations. And then I'm going to talk about 3 areas of inquiry, beginning with adaptive materials, and within each of those 3 topics, I'll touch upon some core research as well as applied practice projects emanating from my practice. Let's start this video here. This video playing in the background is a compilation of data sets, simulations and models, materials that we have produced over the years in collaboration with material scientists, biologists, mechanical engineers, and beyond. Now, certainly biology and material science and other disciplines present very useful conceptual models for us as architects to consider, where form is in constant adaptation with environmental events. Now, I'm very interested in this notion of reciprocity between context and form, and I'll talk about what I mean by context very specifically in a moment. And it's here that geometry and matter operate together as an elastic active ground, what I call a datascape, that steers and specifies form, function, and structure in context. And through direct references to the human body as a point of departure, I'm interested in ideas and topics of flexibility and sensitivity alongside the development of adaptive materials and architecture, where code, pattern, environmental cues, issues of making, geometry, and matter operate together as a conceptual design space. It's the embedding of material systems with biological relationships and behaviors to generate models that on the one hand are natural and on the other are artificial. And on a meta level, Naomi hinted at this, this also marks a shift away from Cartesian formal orders, the spaces that we're used to, that we occupy every day, that have strict borders and boundaries of column, beam, and arch, and towards interiorities, networks, fabrics, and fibrous assemblages that are also plastic, pliable, and open, and one could say, on a meta level, feminine. Now, we frequently start with very simple parts and rules, and through iteration and notions of feedback, we produce much more complex spatial wholes. I'm also very interested in productively tinkering with, misusing machines found in alternate industries from textiles and also industries such as the automotive industry and so on, such as this large six-axis robotic arm. And importantly, these probes are informed by issues of craft and making, the messiness of making, to produce bio-inspired material systems and software design tools that have the capacity to facilitate embedded expressions in our built environment. Now, this is similar to what Detlef Mertens, a very important mentor of mine, describes in his term that he coined, bioconstructivisms, where the emphasis is upon the analogic negotiation of morphological behavior as a dynamic template. I've never been interested in simply scaling up what might be a tantalizingly beautiful form that exists in nature at a particular scale into an architectural form. It's always been about the processes and behaviors that are behind that image, right? The relationships that govern those dynamic conditions that then are married with material constraints and architectural questions. Now, these modes of inquiry are also filtered through material organizations, and importantly, questions that stem from both sides of the fence, so to speak, coming from architecture as well as biomedicine and material science and so on. And so we purposefully resist the post-rationalization of complex form through an approach that engages a materially directed generative design process, or what I call matter design computation. And this has impact in both science, architecture, and engineering. So one of the fundamental questions that governs the work, both in my lab, my teaching, and practice work, is as follows. How might buildings behave more like organisms, responding to and adapting to their built environments? And I firmly believe that in the not-so-distant future, materials will not just be elements and things in our buildings, but they will generate immersive spaces that act upon and respond to affordances in our built environments. So like the very cells in our own bodies, sensors and imagers will learn and adapt, making materials not only smart, but also aware, sensate, and beautiful. And hopefully we will be able to begin to personalize our own spaces and architectures. So I'm going to talk a little bit about some key people that have influenced me over the years. Peter Lloyd-Jones, who is a longtime collaborator, introduced me to the extracellular matrix. And he is a matrix biologist. We started Lab Studio, which at the time in 2006 at Penn, where I was teaching for 6 years, to our knowledge was the first truly hybrid research and design unit that spanned the lab setting and the studio setting. But the big idea here is that half the secret to life resides outside of the cell, right? So you have DNA, which obviously governs form and informs form, but that DNA is acted upon by protein events within this extracellular matrix. So there's a dynamic reciprocity between what's going on within the ECM, right? As we can see in these networking endothelial cells, or these smooth muscle cells trying to network and communicate with each other and move around, that impact code and therefore form, function, and structure. And these are some of the cardinal features of the extracellular matrix. And so this presented to me very early on a series of very powerful ecological models, thinking models, to bring to design. And I'll be referencing some of the work that was produced in Lab Studio, which certainly is a foundation for what I'm doing now throughout the course of my talk. The book that Naomi mentioned, Lab Studio, Design Research Between Architecture and Biology, captures the time that we were collaborating formally together, as well as our teaching. We co-taught a course called Nonlinear Systems Biology and Design for 4 years. And this book really is about methods and modes of thinking across disciplinary boundaries in the production of a truly collaborative space. So it's about tools, it's about projects, it's about research. And I will say one thing that was extremely important to the success of this experiment was the fact that Peter and I took almost a full year to just figure out how to talk to each other, right? Because collaboration there's a lot of buzzwords around collaboration, transdisciplinary, interdisciplinary, design thinking, but to actually really do it and to do it well, it's extremely hard. And the development of trust, of figuring out how to talk to each other, patience, all of these very key things are critical. And so I would join his lab meetings, he would join my studio reviews. He was completely freaked out by the culture of the crit and what we do to our students. I had to let a lot of information just sort of wash over me and focus in on what I could work with as a designer, as an architect, and come from my disciplinary expertise and contribute to core science in a real way. And that was another important thing. We were never interested in turning scientists into pseudo-designers or architects and students into pseudo-scientists, but to, at the very least, produce a truly collaborative space. And interestingly enough, to our surprise, actually, we did have some architects go on to become incredible scientists, and some scientists go on to study architecture and now are doing incredible design. Another important person who I continue to collaborate with, Xu Yang. She is a materials scientist based at Penn. She engages in biomimicry in the true definition of the word. She looks at the feet of gecko, the leaves of lotus plants, to extract principles, features, characteristics from those models, and then to design and engineer new materials that are programmable and adaptive and responsive. And so one of the topics that we have worked on together is structural color. And I'll come back to what that is through the context of one of our collaborative research projects in the lab. And then more recently, Dan Lau, who just is so much fun. He's an incredibly creative scientist and engineer, and he is doing really incredible work with 3D printed hydrogels infused with a synthetic human DNA to get them to respond and adapt based on the very makeup of that material, so what is known as programmable matter. And I'll talk about one thing that we're doing together currently in a moment. So over the years in the formation of Lab Studio, our teaching, and the development of a series of research thrusts, we also importantly didn't start out with any strict deliverables, right? But as I mentioned, we had a commitment to, at the very least, creating a collaborative space and hopefully some new questions and ideally applications in both of our disciplines and fields. Now, since 2006, that has transformed into a series of phases that we typically go through, not necessarily in a linear fashion, but we start with the design of tools, scripts, algorithms to model behavior. I like to think of software as a new type of material, and we might be modeling a particular data set or a material system. We might be simulating that. And then some of those tools are brought into the realm of architectural prototyping. So starting to productively contaminate the process with issues of making, to also responsibly and meaningfully deal with scale, right? Not all of these systems are scalable. And then some of those prototypes are brought into the realm of buildings and the built environment. So it's a purposefully slow process. That also has contributed over the years to a hybrid model. I have three very integrated roles, as Naomi described. First and foremost, as an educator. I think even though my research and my work keep me going and excited every day, the biggest impact that I think I will make is through my teaching and just getting students like yourselves in the audience to think a little bit differently and to go out into the world and make impact. So I teach design, I teach seminars, and then I run my lab and also my practice. And those two entities are distinct. They have their own spaces, but they feed each other. And funding also is distinct. I will say one thing that I've learned over the years, that you don't get NSF funding if you haven't received prior NSF funding. So how does one go about that? You collaborate with people who have NSF funding. And I owe a tremendous amount to my colleagues in the sciences for teaching me how to actually go after those big grants. So I'm going to start with the first topic, now that I've told you a little bit about the foundation, which is adaptive materials, and it really builds upon that fundamental question that I just posed. This project is now a bit older. It's titled eSkin, but I wanted to mention it tonight because it was a very formative project, and it also was our first collaborative project that was funded by the National Science Foundation. And this is the team, which includes biologists, mechanical engineers, and myself. And in 2010, the NSF put out a call for collaborative teams that would rethink our approach to issues of sustainability and specifically thinking about buildings. And importantly, they were very interested in how we might reconceptualize our whole approach to the problem. And I'll mention to you that there's one area in the NSF that funds weird stuff, collaborative weird stuff, and it's called the Emerging Frontiers for Research Innovation umbrella. And so we applied, and we're fortunate to receive one of 10 multi-million-dollar grants, which that kind of funding coming to an architecture program and a PI in architecture is pretty unheard of. So any naysayers that were there before that all of a sudden were saying, this is really important work, you have to do this work. So that was an important turning point for us. And we started the project from this point of departure, which is this notion of dynamic reciprocity. And We proposed that we would develop a thin film technology that could be integrated into either existing facade design of energy-sucking buildings or new facade design. And this is how we started. And so just to give you a little bit of background, this is a smooth muscle cell, a human cell. It's plated on an organic polymer, which is called PDMS, and it's been fabricated through photolithography. And the fabrication pattern includes an array of pillars. And you can see the cytoskeleton lassoing up and around those pillars and the nucleus stained in blue. And we were interested, again, in how changes in this environment, right, compliance, pattern, geometry, materiality, would influence the behavior of the cell, right? So you give it grids, you give it wrinkles, what happens to the cell? And we by no means were proposing to put cells on buildings, right? Cells work very well in our bodies, but they would never work at this scale. They would quickly become confluent and sick and they would die. But at this scale, the cell was our muse, right? We wanted to capture these behaviors, this dynamic reciprocity between environment, material, and this cell, to then design and engineer sensors, right? So not cells, but sensors that could learn and adapt over time in their particular contexts. And so that's when we started to work with structural color. There were many, 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 many parameters and topics that we could focus on, but we decided to focus on structural color as a point of departure in relationship to the behaviors that these cells were exuding. And so what you see here is an example of a predefined geometric pattern, and it's embedded within a shape memory polymer, an SMP, and it's displaying structural color change under deformation and recovery. And so literally we were stretching these pieces of the E-skin material, and what's happening is that as this material undergoes a mechanical transformation, so I stretch it, I squish it, those pillars or holes would change their orientation. So imagine all of those pillars, they go from being normal to the surface, and then they start to do this, right, when you're stretching it, and therefore the light that's interacting with that material reflects and refracts differently, and we in turn perceive a change in color or a dynamic switch from transparent to opaque. So it's not about pigment. And so this is the expertise of Shu, and I was operating as the designer in terms of pushing the project forward. Through a series of invitations to exhibitions, we were able to start to tackle the problem of scale. Most of my collaborators engage in fundamental research, so that means it's not that they're not interested in application, they just don't do it, right? They have far too much to do with fundamental research. And as the architect on the team, I was like, wait a minute, we proposed we were going to make these building skins, and how do we get there? And so we had these invitations, and I was able to push the team through prototypes, developing our own software to actually render the E-skin data, looking at multiple scales, and then a prototype that we're all extremely proud of, which took us almost 2 years to produce, entirely from scratch. We were interested in creating a prototype at the scale of a human that could potentially simulate what a building component could do, that would dynamically switch from opaque to transparent and then also display a gradient of color. Now, I mentioned not all of these materials are scalable, right? So we quickly found out that these little swaths of E-skin, to simply fabricate something this big, right, would not only be prohibitively costly, it would take an enormous amount of time. And so we started to think about other materials that exhibited the same characteristics and features of the PDMS, that organic polymer. And so we started working with what are called nanocolloidal particles. And you find these little guys in certain seashells, such as what's called nacre, milk products, other natural systems found out in the world. And so this was the finished prototype, again, made by us working together at the lab bench side and in the studio. And just to give you a little bit of background, there's an array of sensors that detect a change in light intensity that then send a very small regional charge to these components, which are formed of two sheets of conductive glass called ITO glass, and those are containing a sandwich of those nanocolloidal particles. And so that little voltage changes the packing density of those little particles, and that in turn changes how the light is reflecting and refracting, and we perceive a color change or a change in transparency. This is now part of the permanent collection at the Frock and was part of the 9th Archilab titled Naturalizing Architecture. This was our vision and where we're at now. After doing 4+ years of fundamental core research together, we're now looking for other possible grants with industry partners where we can really start to realize what our original vision. From start to finish, to think about how a material like this could become an industry-ready product and where we would see it in our built environments, it really takes between 12 to sometimes 20 years, because there are all kinds of hoops to jump through, not only funding, but also code restrictions, litigious issues, builders who don't want to work with it, and so on. So a lot of interesting topics that emanated from this project that then informed other research. And very briefly, we were fortunate in 2013 to continue the work from eSkin in a second multi-million-dollar grant from the NSF, again from that weird umbrella, Emerging Frontiers for Research and Innovation. And this time the topic was on origami. And so we pitched working with kirigami, which is like origami but with the addition of cuts and holes. And we were interested in leveraging all of the benefits of eSkin, but moving away from a single swath of that material into a larger system that had hierarchy that would also fold and adapt and have a degree of integrated behavior. And this is when I met Randy Kamian, who is a theoretical physicist, models crystalline materials and squishy things, and he was the PI on this project, and we worked quite extensively on the development of tools and understanding the geometry. So you're going to hear a little bit from Randy on kirigami in this short video.
Kirigami and origami are closely related. In origami, we usually focus just on folding the paper. In kirigami, we are also allowed to cut it. Cutting it adds a new dimension to the structures we can build. Without folding paper over itself, it is possible to make three-dimensional pop-up structures. In fact, with a little tape or a staple, we can make the structures completely rigid, or, left as they are, we can use them as levers and valves. By following a simple set of rules, we can keep not only the paper from stretching, but also all the bonds or edges in the original hexagonal sheet from stretching. We can see where the paper pops up or down by seeing where the hexagons become pentagons or heptagons, respectively. Put together, these folds and cuts can be made into complex, variegated structures.
And then we began to look at those geometries against material constraints in terms of the work coming forth from Shu's lab. And we constantly were moving back and forth between the production of simulations of those geometries, looking at possible distributions of cuts and folds across global geometric systems, and then also importantly prototyping as experiment. And so this was a room scale project called the Color Folds, where we began with a whole series of paper models, as well as looking at the promise of a degree of learning within an assembly, so deploying a simple learning algorithm. And Color Folds took nearly a year to produce, and it was installed for about 6 months. We continued to work with this as an active experiment, but you can see here we really jumped in scale. But this is the same material, right? But because they're at different orientations, we get a radically different display of color in terms of its wavelength dependence. I typically shy away from working with physical computing and mechatronics, not because I'm not interested in it, but we focus more so on the materials themselves and how they can respond and adapt. But it made sense with this particular project, but I learned why I don't work with these systems. But we made everything from scratch. There's a network of nitinol spring wire that allows for the components to fold and unfold. Boards with thermistors. Each component had its own little board that we could communicate across. And for those of you that have done any work in this area, our biggest issue was just figuring out how to power the entire thing. And so actually when it opened, I ran to the local automotive store and bought 2-car batteries, and that did the trick. So that's why we have 2-car batteries in my lab. As you can imagine, jumping to this scale, paper, in terms of its thinness, moving from paper to a 6-millimeter extruded polycarbonate that's CNC'd, the hinges quickly became a problem, right, to address. And so we went back down in scale as of late to think about how we can leverage pattern and geometry to get global response, and to also work with 3D printing. And this is where Dan Lau and his work in 3D printed hydrogels infused with synthetic DNA has come in a pretty interesting way. So our work in adaptive materials certainly has informed this second topic, which is looking at non-standard structures and adaptive structures and form. And when I say adaptive structures, I don't necessarily mean that they're literally moving, but learning from the dynamics of particular biological systems and forming bridges with modes of making and fabricating primarily through 3D printing. And it was in 2009 that we purchased our first powder-based printer. And this was when I was still teaching at Penn, and Peter and I were collaborating and teaching through Lab Studio. And I was interested in working with the 3D printer not as a representational device, but to literally rapid manufacture one-to-one scale parts. And Peter and I were also very interested in notions of, what would it be like to hold data? How might that influence the scientific process? How might that allow the scientist and the researcher to project into the data and the problem at hand in a different way, in a spatial way? We were also interested in thinking about the production of non-standard components and maximizing the build bed, right? So the parts could be quite large, but then when they were assembled, we would have an even much larger whole. And so we were producing a whole series of prototypes and investigations of multicellular structures. And it was during that time, in August in Philadelphia, when we were working on a project for SIGGRAPH, that I realized that all of my knowledge, like literally a body of knowledge in clay, in dirt, in ceramics, had some value. And I thought I had long since left working with clay. But I just sort of quickly realized that we could perhaps do something pretty interesting here. And so I took out the proprietary media. At that time, this was a Z-Corp machine. It's now known as 3D Systems. These companies don't make money off of their printers. They make their money off of their media. I didn't tell them I did that. I didn't want to do anything with my warranty. But what you see here is our own recipe of a high-fired dry stoneware clay body mixed with a little bit of sugar and a little bit of maltodextrin from your local grocery store, which facilitates the printing process. And these are our first successfully printed greenware clay parts. So you can see here the same part printed in the proprietary media, and then here in clay, bisque fired, and then glaze fired. And since that summer of 2009, that has formalized into both a teaching and a research trajectory in my lab and in my studios and seminars on the topic of digital ceramics. So looking at one particular medium alongside contemporary methods in digital fabrication, but importantly, considering the role of the component and the non-standard in that. And in the lab, more recently, we have been pushing polybrick, and we have a lot of scientific papers on my website if you're interested in learning more about the technical background of any of these projects. And this first iteration, Polybrick 1.0, we were just simply trying to figure out what we could do in terms of thinking about a porous brick, a non-standard brick, and then more recently pushing that into 2.0, where we're working with human bone models as a set of design drivers to optimize for load paths, as well as to create wall systems that are extremely light and porous but very robust. And then currently working with Dan on a DNA glaze, which we've had a lot more success than he and I initially thought, where we're interested in hopefully a glaze that could alert people of a contaminant in the environment, and at best perhaps even clean that local environment. And Dan has found that clay actually is an incredible host for life. So I'm going to play a little video, a short video that summarizes the polybrick work. The production of ceramic blocks and tiles has a long technological and design history. Ceramic modules of standard measurement have been used as building block and replacement of stone for many centuries. Ceramic bricks and tiles, so ubiquitous in their application in the built environment, have surprisingly lacked recognition as a viable building component in contemporary architecture practice until now. Polybrick, our latest endeavor under the topic of digital ceramics in the Sabin Design Lab at Cornell University, showcases next steps in the integration of complex phenomena. This work includes advances in digital technology, 3D printing, advanced geometry, and material practices in arts, crafts, and design disciplines. The first phase of the Polybrick series features the use of algorithmic design techniques for the digital fabrication and production of non-standard ceramic brick components for the mortarless assembly and installation of the first fully 3D printed and fired ceramic brick componentry. Polybrick 2.0 is generated with the rules, principles, and behavior of human bone formation. This allows for the production of variegated bricks that are light and porous at the top of the wall and dense at the base to carry load and maintain efficient structural integrity, while also amplifying material and formal expressions. Polybrick 3.0 takes our material investigations to the next level. Synthetically designed with advanced bioengineering, these biobricks will exemplify the cutting edge and future of biologically steered clay and ceramic building blocks in architecture. The two prototypes utilize 3D printed clay, hydrogel, and synthetic DNA. As you can see here, a unique ID stamped with DNA in the form of a C for Cornell is fluorescing within the polybrick clay body. Brick stamping has a long history where variegated size, shape, and stamping indicate place, date of construction, and type, and thus serve as invaluable historical documents. With our unique DNA stamps and glaze, we explore the possibility of live signatures and dynamic surface techniques, coupled with non-standard bricks in the context of living matter and digital ceramics. We just published a technical paper on that last project, which is very new, in a current volume of additive manufacturing, if you're interested in learning a bit more about that. I'm super excited about where we're going with that trajectory. A project Polymorph, which was also part of the 9th Archilab, so the eSkin work was in Archilab as well as Polymorph, is probably the most mature project to come out of the digital ceramics work, certainly the largest, And for me, this project was an opportunity to synthesize, at that point, about 8 years of deep inquiry and collaborative research on cellular networks and cellular network morphology with Peter into a point of departure for this large spatial ceramic system. And I was interested in, thinking about what does it mean to spatialize a node? How do we learn from the elements of surface design in multicellular systems? In my case, studying cells networking in the human body, and specifically endothelial cells networking within the human lung. How do we learn from those morphologies in the way that surface is designed to form a sheet that then folds and bifurcates to form a tube, and then larger, more hierarchical forms? And how do we explore that with very, very simple parts? And so we settled on 3 different parts that had about 250 different ways of interweaving. And this is a drawing that highlights how that worked. You can see in the background a very, very, very simple system of a equilateral triangle and an isosceles triangle, right? So the key was the arms always had to meet, but there are multiple ways that these 2 interweaving surfaces could work. In the early rendering, we went through a whole series of different iterations, thinking about possible final global forms. And then we began production. I hired 2 ceramic artists to lead the production effort. I really wanted people on the ground that knew the material. And here we used the 3D printer not to directly print the components like with Polybrick, but to optimize for mold design. And for any of you in the audience that have done any slip casting, you know that to produce a simple, elegant 2-part mold with a part that has complex curvature, it's very difficult. And so we wrote some simple algorithms and optimized for that, printed the 2 positive halves, and then generated about 20 plaster negative molds from that. So the 3 parts had 20 molds apiece, so we could cast upwards, 90 to 100 parts a day. So we hand cast everything in-house, as well as bisque-fired everything, and then I outsourced the glazing. And this is how everything was shipped. At one point, the curator called me and she said, "Is there a plan B if things don't arrive okay?" I said, "No, there's no plan B." But there's about 2,000 of these, 2,000 digitally produced and hand-cast parts. I'll let you take a guess as to what the black string is all about. And here you can see it's starting to take shape. So slip casting was important to the project and important to the structure, because running internal to all of the hollow parts is a continuous network of stainless steel cable that's in tension, bringing all of the ceramic components into compression. This little detail was quite important. Ceramic doesn't like to touch ceramic in compression, at least in this way. And I actually found that pinball bumpers were perfect. It's now permanently installed in this skylight here called the Turbulence, which is the new addition to the Frock by Jacob and McFarland in Orléans, which is about a 50-minute train ride outside of Paris. If you have a chance to go to the Frock in Orléans, go. It has one of the most extensive drawing and model archives of experimental architecture from the 60s archigram to now. Really amazing work. And Frederic Migrou and Marie-Ange started the Archilab series. Here you can see sort of halfway through the installation, I think we took the award for the longest installation period. All of my work has a kind of an aspect to it where we incorporate very sophisticated digital methods and modes of thinking, and then there's always a very analog, slow mode of making and assembly. So you can start to see the kind of lacy woven configurations, the networked topologies starting to emerge, and then some final images of it fully installed. I don't think I will ever suspend 2,000 pounds of ceramic into the air again. It's still there. Nothing has happened. But about halfway through, or we were almost done with the installation, Frederick Migru came out, and this just kind of captures the changing light throughout the day. And he looked up at me and he goes, "You are really smart." And I was like, oh no, what is it? You know, if you know Frederick Migru, you don't really want him to say that. And he said, "That's not going anywhere." And I had actually thought about how we might take it down, but fortunately he really loved it, and so they decided to have it join their permanent collection. So this is polymorph, and it isn't a sphere. It has 3 holes in terms of the inversions, but was really proud of this project and the sort of questions and inquiries that it opened up for us. So I'm going to transition to my last topic, and obviously there are themes that carry across all 3, but it also highlights kind of different types of scales, differences between lab work, teaching, and what I'm doing in my practice. And this third topic deals with adaptive environments. So really starting to push into that third category, questions of architecture, of the built environment, of beginning to architecturalize and spatialize these experiments and prototypes. And I'm going to present one project, which is Lumen for MoMA and MoMA PS1. But before I get into that, I'm going to reference a couple of projects that were really important to the development and I think the success of this project that was installed in the PS1 courtyards during the summer of 2017. As you can see, it takes an army to pull this project off. The amount of time, the creative budget, and just the intense constraints that one has to take on to successfully pull off the project is pretty amazing. So this work, in terms of specifically incorporating textiles, and even more specifically working with knitting, started with a commission in 2012 from Nike for a pavilion that was I called it the My Thread Pavilion. And Nike invited 6 people from around the world to be a part of what they called the Flyknit Collective. And they were interested in how, and it included architects, designers, and artists, and I represented the states. My city was here, New York City, and they were interested in how we would respond to, riff on, and take the core benefits of a particular technology that they were about to launch back into our own fields, and that was the Flyknit. So all of you are familiar with Nike Flyknit. So topics such as performance, lightweight, flexibility, sustainability, form fit were used as sort of inspiration and points of departure. And so out of the 6, I was the only one that proposed to work with knitting, and I thought it was sort of obvious, and they were surprised by that. And so I was interested in working with the simplicity of knitting processes and the complexity that it allows for, wedded with human bio data sets as a set of design drivers, not as a mapping or a representation of that data, but to really look into the kind of hidden structures and spatialities of that data coming from the human body, and attaching that very specifically to parameters of knitting to realize and spatialize pavilion architecture that could somehow allow us to inhabit our own bodies in a new way. And it was also the first time that I started working with these high-tech responsive fibers, photoluminescent and solar active, which definitely emanated from the work that I was doing in structural color with Xu Yang. And so the photoluminescent, what's happening, just kind of high level, is those fibers absorb UV, so energy from the sun or a UV light source. And then when that energy source goes away, the photons within that fiber get agitated and they release that light. So it's released as a sort of glowing light or knitted light. The solar active fibers change color immediately in the presence of UV. So what is white changes to kind of a pale yellow, blue, and so on. So that was a critical project. There were a couple of other projects I did for Nike, and then in 2016, a pavilion project for Cooper Hewitt as part of their triennial, their design triennial titled Beauty. And here I wanted to, again, learn from the years of investigation into cellular systems as a way of thinking through a design process and the production of form, and move away from the frame that you saw with my thread where everything's sort of pulled into tension, and to think about a freestanding structure that would have a double surface, which you can see in some of these early sections. And it was also then that I started working with Arup, and specifically Clayton Binkley, who is a structural engineer whose expertise is in fabric structures. So we did a whole series of swatches, mechanical tests, stress tests, to then take that data and put it back into our tools. I mean, you know, there aren't design tools out there to work with these types of materials, so we've had to create our own. And these are some final images of that project, and you can see here in this detail the density of that double surface, where the conical members actually structurally are springs, right? And I should mention that I've been working with Shima Siki since 2012 on the knitting and really innovating together in terms of scale, complexity, material palette. And they're at the forefront of what's called whole garment knitting, which is 3D seamless knitting. So one could say that knitting in a way is an early example of 3D printing, additively layering link by link, row by row material. And it was this image that sort of haunted me as a point of departure for Lumen, and this was that interior sort of poché space between the outer and inner surfaces of polythread. I'm going to play this in the background as I describe some of the points of departure for Lumen. So as many of you know, the project brief for PS1 requires that the finalists produce a proposal that addresses issues of shade, right? It's quite hot in the summer, as you know, in the courtyards. Water, for similar reasons. Topics such as recycling and sustainability. You know, what kinds of materials are you going to use? Where will they go after the project is over? And importantly, when I was competing and made the shortlist, Sean Anderson, who leads the program now, was interested in topics of materiality and transformation, which obviously resonated a lot for me. And I was interested in how the final project could operate as an environment instead of an object or form, that it would be highly transformative throughout the day and night, that people would have different experiences if they came during the week to have their lunch versus during warm-up when 7,000 to 8,000 people come to listen to amazing DJs from all over the world. And I also knew that in order to be strategic, if we were going to win, I needed to leverage a body of work that I felt extremely confident about. And so I knew that the material system that I've been developing since 2012 with the knitting and the responsive fibers was really ready to go outside, right? And so no longer solely working with indoor lighting treatments, but actually starting to work with the sun. It also requires a seating component, and so we did, the spool stools were recycled, deconstructed, cable stools, and the prototypes were woven by my robot in my lab. We did a whole series of form finding tests. We did some solar analysis and quickly found it's very sunny in those courtyards, but it did influence the density of the cells a bit. And there are two 42-foot tall tensegrity towers, which I'll go into detail in a moment, and a smaller one in the smaller courtyard. So some proposal renderings highlighting the change from night to day, the photoluminescent to the solar active. We also created a full VR model, which these are snippets from. And so Glenn Lowry, the director of MoMA, and the members of the jury were able to put on VR goggles and experience Lumen, which was important to me that they really would get what I was going after. It wasn't just a canopy, it was a canopy that would come alive through people's participation. And so this notion of materiality as being something that's co-produced, right? It's not just the responsivity of the materials, but it's also the space that's produced through people's interaction. We used the site as a part of the structure, so the canopies are stitched into the existing concrete walls and held in tension, and then pushed up with the tensegrity towers. We had to do actually a lot of analysis on whether or not these concrete walls could take the amount of tension running through the system. And it was heavily used throughout the summer, both during the week and also on the weekends. And again, some early drawings just looking at in section and elevation how those changes could be represented, and some final images of that. In terms of the components of the material palette, there are about 5 different types of components. There are flat cells with basically a lip, so a bit more shaping, and they would provide a kind of flutter through the whole canopy. So when it was even slightly windy, you would get this kind of flutter rippling across. And then zones of cones, for example, this was a misting corridor. So there's a misting system that runs along the top of this entire network and then comes down into the cones with misting nozzles with a series of sensors that would flip solenoid valves so that as you're walking through this whole thing, it would cool down the climate. And it actually was quite successful in doing so. And so the 2 sensors that we had integrated in the largest canopy were part of ongoing work in my lab. So I also leveraged work that we were doing in the lab properly in terms of research to then test it on Lumen, and the sensors were one such thing. This just describes what we did with the recycled spools, CNC'd the tops and bottoms, which formed a cog, which we could then weave a diagrid structure across, which then created a whole varied set of patterns. The tensegrity towers provided a kind of third element of dynamic conditions in terms of working with tensegrity. So all of the ropes are in tension, and then the compressive members, including the main mast, work reciprocally with that. Just to add a little bit more complexity to everything, but we learned a lot in both the engineering and the design of that, and I have learned so much from Clayton and working with the Arab team and vice versa. It's been an incredible collaboration. So here you can see the solar active fibers starting to emit a kind of pale color. I should mention that Daisian has done the finishing and the sewing on my projects for the last 5 or so years, and I mentioned the kind of slow analog phase. So all of the components are digitally knit. They have an ID that follows them from the design phase all the way through the final production. And they work with a 1-to-1 scale drawing. So we literally plotted at 1-to-1 scale the entire canopy. So this is the entire courtyard, about 150 feet across and about 90 feet in this direction. And so they joked that they started in Washington State on the West Coast and they ended on the East Coast. And here you can see it fully installed. Some of the details of the stitching. I mentioned the creative budget. A big part of this project is creatively finding ways to get people to do things for free. and to donate materials and to innovate around details with off-the-shelf hardware and so on. And this is the misting corridor seen from above, so you'd walk through here and you get misted, and some of the photoluminescent fibers starting to glow at dusk, and then here amplified at night with a lighting treatment that came on at night to really augment that and amplify that. This is the smaller courtyard at night with a view into the larger canopy structure. Again, some views of those photoluminescent fibers, and a great view of one of the larger towers. The erection of each of these was fairly, I'll say we incorporated some creative rigging late at night so nobody would get worried and freaked out about what we were doing. But there's a mast at the top that allowed us to adjust the tension on site and just refine it, and then also U-bolts at the base so we could cinch those up. And we actually pre-stressed all of the ropes on site with basically a giant stretcher so that once this was up, they didn't continue to stretch, as we didn't want to have to go up and do that all over again. These are ropes produced by a company in the Northwest that typically makes fishing nets and fishing rope. And I think for me, the best part of this project was simply seeing how people used it and how they fell in love with it, and the creative ways that they engaged with the project in all of its scales, including during warm-up. This was an incredibly frightful day for me. I think I was over here in the corner in a huddle. And also served as a great backdrop for the evening parties during warm-up on Saturdays. So I'm going to stop there at 7:30. I've only shown you a kind of cross-section of our work. If you're interested in seeing more of it, you can visit our websites. I don't work alone. I hopefully have said we for the most part throughout this lecture. I'm fortunate to work with some amazing students and colleagues and research associates and senior designers in my practice. And we've also been very fortunate to receive quite a bit of funding to really push the work to the next level. So I'm going to play this film in the background, which is a short, basically documentary of Lumen that highlights its construction and also its use. And I'm just going to turn the sound off. But with that, thank you, and we have some time for Q&A and discussion with Tom.
Thank you very much, Jenny. That was really, really tremendous. Please, center stage. We will, my name is Tom Barrett. I'm Associate Dean for Academic Affairs. I'm thrilled to, I'll turn this on as well. Got it? You have that one. Somewhere in here there we are. We will open this up to questions from our audience, especially from students. So really, if you haven't thought of a question as in any sort of form, don't hesitate, please. Maybe just to kick some things off.
Yeah.
I realized a few days ago that I thought I knew your work very well, and then I did a bit more research, and so I looked through your 400-page book, which is tremendous. And what struck me is kind of paradigmatically how serious your work is in terms of a cross-section or intersection between architecture and the sciences in sort of broad senses. And it's really interesting to hear how you talk about the different reciprocities between the design lab or design research lab or research design lab and your office or studio, and between teaching, research, and practice in kind of more conventional kind of categories. And I think this is, I mean, you describe that as sort of hypothesis-led, And I'm really curious how, on one level, you negotiate the kind of rigorous methods that are in the book, really presented in a really scientific sort of mode of analysis and description and sort of feedback and critique, and how you negotiate the sort of precise methods with, when one looks at the work, and this is what I learned by reading your book, is the kind of experimental design kind of modality of the work that produces, that seems like it's produced in a sort of context which is sort of not so scientific, but actually really much more inspired by a pursuit of innovation without sort of the methods. And it's, you know, as we see these things dangle in the background. And what seems really interesting is, and maybe in the title of your lecture as well, the kind of new paradigms of making. And Detlef Mertens, as a well, not so much a preface because it was an article essay written quite a few years back, writes about the problem of predetermination and the relationship of self-generation in design. And Antoine Piquant, writing specifically for your book, not as a kind of essay written long before, working and describes a kind of your work being deeply embedded within history, a kind of history of the organic and biological relationships to architecture, and how he talks about the path-breaking contribution of your work, or more generally about the kind of working paradigmatically of having to still work within a paradigm as a kind of guiding set of principles, with a deep-seated everyday sort of intentionality to break with those traditions and those histories. And I'm really curious, you know, how do you negotiate the sort of deep historical context of your work with a will to break from that history, you know, in terms of the deliverables and the design effects and what it is we might experience?
That's great. So, I mean, some of my heroes, just building upon your references to Detlef's piece, in design include protagonists like Robert Le Ricolet, who was trained as a structural engineer and designer, but then ventured into architecture and taught in the Northeast in a number of schools. And he was obsessed with looking to nature for design models and inspiration, but approached it also from an analogic point of departure, to leverage materials as a ground for studying these dynamic processes. And, you know, he's the father and pioneer of corrugated sheet metal and the space frame, right, which are pretty big inventions. But he importantly didn't start out by saying, I'm going to make the space frame. He started out by obsessing over the exoskeletons of radiolaria and trying to figure out how those worked, and would then produce all of these models to look at what he called the beauty and failure, how force flows through geometry and matter. And so that way of, so the point being, and that's one of many important protagonists that have inspired me. And so obviously that mode of thinking and turning to nature for design inspiration is not new, and there's a tremendous history to learn from. But what we are in the midst of, and Mario Carpo is writing about this, and others, is the biggest paradigm shift to hit architecture since the medieval period, which is repositioning architects as makers, right? So if you think about, and again, Carpo has some really amazing essays on this and texts. If you look at, say, Brunelleschi, another important protagonist, designing and making and building on site in real time, right? So late medieval period, designing and making and building the Duomo, where he's collaborating with artisans and craftspeople and designing as a kind of inextricably linked set of decisions. But you jump a generation later to figures like Alberti, who hands us plan, section, elevation, our modes of notation in terms of communicating information about form. And he effectively removes the architect from the making, right? So we author the drawings, and those notations are interpreted by others. So the building becomes a copy of what we've authored. But now, with robots and 3D printers and all of these machines, as facilitators, we can work in a way where material, geometry, pattern, context, human interaction are a set of, again, inextricably linked constraints and questions and parameters. And so that, for me, is why I turn to biology and science, because it's not, again, simply to just produce these organic forms, but I think there's some really powerful ways of thinking in this new paradigm. And working with scientists has made me a better designer, a more rigorous designer. But we project into the world, we put stuff into the world. So the process that you mentioned, there are different types of rhythms. You know, in the lab, we might, like with eSkin, be chasing something very specific for 4+ years that has a slower arc and maybe fewer deliverables, or the deliverables are different than, say, a project like Lumen, which is subjected to a budget, to schedule, to working with manufacturers and so on and so forth. So there are different questions that are posed. So in the doing of the work, it's linked in terms of the thinking, but I think I'm of the opinion that architectural research shouldn't necessarily have a deliverable attached to it, that it has, it's not necessarily a building. It could contribute to a building, it could contribute to a material prototype, but it doesn't have a particular deliverable, and therefore it allows for kind of iterative and rigorous inquiry within a very constrained scope that produces innovation. And so that's how I kind of separate the different modes of working across those boundaries.
And I think in a paradigm transition or towards new models and methods, even new materials, new media, of looking, as you said, the long history of looking towards nature as inspiration, or working or design with nature, to quote Ian McHarg, and this whole arc of trying to discover our relationship to nature, or architecture's relationship to nature, or do you find that there's a transition that's happening which sees the design project itself, the media, the matter, etc., as having a nature, as being part of nature already, or natural in a kind of classification? Not to say that nature is something out there that's pre-exists all of our kind of mineral and synthetic efforts as architects and all the civilization that we've produced on our planet, but that actually what we're making is already designing nature itself, and that fusion between the synthetic or the artificial is that our capacity is not so much the immediacy, as you say, to produce, but that we can work on that sort of material level of the material science that you're working at. You can work with the creation of sort of effects which previously were just not possible, that have a sort of lifelike and animate set of qualities, rather than architecture and materiality being understood as sort of something dead that only gets lifelike when we fill it up with activity.
I can completely agree, and I also think that's why design is so massively important to doing science right now, and continues to be even more important, because our ability to synthesize to think through relationships within that nature is incredibly important to science. And that also has to do with, I think in part, not entirely, but in part, and how the practice of science is radically shifting in the context of big data, right? So the scientific method of producing the hypothesis and then in a very reductive manner, producing data that's repeatable to a certain extent, that's getting completely flipped upside down with big data, where there's a shift towards looking towards trends and behaviors across fields, and so design and what we can offer actually has, I think, a place there in that nature, which fascinates me.
Maybe we can open it up to questions from our audience, students in particular.
Sorry, just kind of a simple question about seeing the other side of, we see so much about the surface, the membrane, the knitting of even the process itself as a kind of result of what you do, right? But could you talk a little bit more in terms of the spaces you see or explore or create within this web that you weave between process and material?
Yeah. So one way I would address that important question has to actually do with Lumen. So many people either would write to me or would find me when I was on site, or what have you, after it came down, and would say things like, I wish that project was in my child's playground. I wish that project was in the hospital that I've had to frequent. I wish that project was in the park that I go to. And so people would talk about how they felt calm, how it created a kind of transition moment in their day. So some people might call that like a biophilia. I really don't like that word. But there was something about the nature of that project that resonated with people that I'm really deeply interested in and committed to. I'm not quite there yet in terms of articulating exactly what that is, but I do think it has something to do with the fact that it is continuous, it is informal. As I discussed at the beginning of my talk, it produces a more feminine form that is produced from elements that are not our typical kind of Cartesian masculine elements that do produce hard edges and borders and conditions. And so I'm interested in the potential hybrid of that, right? That will everything look like Lumen? No way. But could there be a hybrid where these new paradigms of making and the results that they produce generate events and moments of pause and interaction with humans that has some relevance? So.
Other questions? Back.
First of all, thank you for the presentation, and kind of following up on where you left off just now. You talked a bit about, towards the end of your presentation, you talked a bit about like driving forces towards like analysis and architectural like research, and like not trying to hold yourself to deliverables when sort of going through that exploration. And so I kind of want you to talk a bit about what's sort of your driving force in this exploration of science and architecture and the intersection, and how do you stop yourself from doing your analysis just in a way not to just sort of, because some of the forms I see in this certain discipline when it comes to like biomimicry. Some of them feel very generic and just as a form of trying to like shift away from Cartesian sort of architecture. So how do you stop yourself from doing this analysis just not on the basis of doing something different, but I think you start to show in a bit of your work sort of the basic principles about what materials can do, so what kind of drives you in a way that stops you from sort of researching on a basic level and kind of heightens your research?
Well, I mean, first of all, I'm a maker at heart. I like to make things. We make messes in my lab. We produce a lot of stuff. So I'm really invested and obsessed with how all of these emerging technologies and inquiries meet the material world and the built environment. So that's the obsession, and also the question. The kind of I'm very comfortable with ambiguity. And not knowing necessarily what the final result will be. That doesn't mean that we're not incredibly rigorous and meticulous in the core research. But I guess there's not really a kind of stop and start, like I do the analysis and then I put my other hat on and we produce the project. There's always analysis and core research running alongside what we're doing in my practice, and they sometimes cross over and touch each other, and other times they're just sort of moving along at different speeds. So it's not linear like that in terms of my design process at all, and that's actually the hardest thing to teach. The tools, yeah, there's a learning curve, but the hardest thing to teach is to get students to really design in a systemic and relational way. And that means moving away from composing, right? So if we think about kind of, just as a simple example, the partie diagram, that the big idea that you design towards, I'm saying and challenging, well, what if we flip that upside down and say that diagram emerges through a whole series of constraints and systems and relationships that inflect each other and inform each other. So, yeah, it's not a start and stop in terms of the research happens and then the project happens. So I think that is why the work bears some success in, it's not about just being different or innovative. It's a deep commitment and obsession with how science and architecture and these technologies, and importantly, the human, can work together.
I went to the Cooper Hewitt exhibition, and I thought it was beautiful. But what I noticed is that it creates its own world when you're inside the installation, basically. But it doesn't, in my opinion, combine with the architecture itself. It creates its own world, and you're almost separate from everything else that you just experienced, which I think is beautiful. But as architecture students, what is the takeaway from this, basically, that I was missing personally, that we use in our own studios, that we use going forward into the industry?
Yeah, the Cooper Hewitt was a hard space to work in.
Yeah.
It was probably the toughest set of constraints I've ever been faced with. And that had, that was an exhibition, as you know, that had multiple projects. In fact, I was installing it with my team just after they had set up NARI's 3D printed glasswork. So here we are with active bending structures, trying not to break anything. So yeah, I agree. That was a tough space, and there was a ton of work in that space. The second installation of it at San Jose was better because it was just a larger space, and so it flowed a bit better. I think for me, the takeaways that I hope you consider in terms of moving forward in your own work now, and also as you think about practice, is on the one hand the importance of hybrid thinking, right? And realizing that architecture increasingly so the practice and also the discipline demands hybrid thinking and collaboration. On the one hand, the issues and crises that we face are so big, and for us to think that we can try and tackle them alone is ridiculous. And so incredible things happen when you bring together a material scientist, a biologist, a mechanical engineer, an architect, and so on. So the relevance of collaboration and hybrid thinking and how that can inform your design practice. I also think, there are all kinds of different ways of considering how, for example, emerging technologies might impact what you do. Some of my students, one student leads the advanced modeling group at Front and has taken stuff that he learned working with me into pretty amazing levels of facade design. Other students have gone out and worked in similar units at major firms like Foster & Partners. So there are different levels of interrogation and bringing this thinking into practice, where I'm very happy to see that those specialist modeling groups are actually starting to dismantle. They're no longer just the geometry fixers and the tech guys, but they're dismantling and becoming integrated into the design teams. And I'm talking about kind of mid to large scale firms, because it's not just the tools, but it's a way of thinking in a design process that has, I think, major relevance to it. So for me, it's the thinking. It's not necessarily, go out and produce work that looks like this, but go out and be responsible in the way that you think through a design process collaboratively.
It's an interesting question, that the sort of takeaway, which when one considers research in any industry, there may not be an immediate impact, and the impact often takes several years, maybe even a couple of decades, especially in the context of doing more experimental installation design, and how that might relate to the conventions and the mainstream of architecture may take some time. But I think your examples of these specialist groups within larger practices, which used to be understood as incubating certain kinds of techniques and knowledge that would be fed into projects, are beginning to become mainstream. So even on a kind of very large scale commercial kinds of practices, are distributing those sorts of bodies of knowledge, tools and techniques in ways that they are becoming mainstream. So it could take a little bit of time for the more cutting edge fringes of architectural research to actually become part of a kind of mainstream architectural practice, methodologies and tools and techniques. Sorry, other questions?
How's it going? Well, it is loud. First, again, thank you for the wonderful lecture. I was just two sort of questions here. First off, what's been one of the most challenging sort of problems that you've had to face in your career? Not only disciplinary, but also as working in a team generally. And secondly, going back to sort of e-skins and the non-standard structures you were talking about of the polybricks. I was just curious if or are you guys working on any current projects of bridging the two, sort of like with this focus on biomolecular structures, but also sort of a function to them in the sense of making them breathing or living, so that the buildings could then become living buildings or something along those lines. Just wondering.
Yeah, sure. Thanks for the questions. So for your first question, in terms of challenging moments, I think early on it was tough I mean, surprisingly, even though there's a long history of architects working with nature and being inspired by nature and so on, there was a lot of pushback from colleagues, both on Peter's end and my end, when we were starting Lab Studio. And that was lonely. It was tough to defend at times, but we persevered, and we were fortunate to have some key people really backing us high up. People like Detlef Mertens, who was my chair. There was no question that it was massively important in his opinion. We had the Dean of Medicine saying, "This is the future, and I'm going to give you space, and I'm going to give you some seed money." We had the director of the Institute of Medicine and Engineering saying, "This is the only truly collaborative lab on campus." Right, so we had these really important figures saying, "Carry forward, you're gonna, this is amazing." And those people continue, some of those people continue to be involved and impact the work in various ways. So I would say probably the hardest thing has been a frequent loneliness, because I've had to craft this new path and do things like educate my business administrators on how to manage these grants. I mean, everything is just like, so it's exhausting. But now, 15 years into it-ish, it's getting really exciting. So I recently launched this new degree program, which really formalizes the work. It allows students to come in to be funded, to work on the core research, to develop a thesis. So those things are super exciting, and especially to see where my students are going and what they're doing. I mean, it's, they're going to get more sleep than I ever will. But so that's been probably the biggest challenge. The breathing buildings. Easkin, I mentioned that I would say that the specific material Easkin is not being carried forward currently, but all aspects of the characteristics and the specifics of structural color, and that continues to be pushed forward in a lot of the core research projects. In terms of materials that eventually, hopefully, can be integrated with buildings. I actually have a permanent pavilion that is going to open on Cornell's campus this spring that the College of Human Ecology commissioned, that will feature that at a large scale, which I'm super excited about. The bricks have a way to go. They're at 1-to-1 scale, which is awesome, but there's some finessing to do with the material, and you can't imagine how many hoops one has to potentially go through to actually get that to a building site, right? I'd love to do a larger scale outdoor structure with it. I think the proof of principle would come through that potentially.
Thank you.
Maybe one or two more questions, and all the way in back.
Hi. So maybe as sort of a follow-up question to the previous 3 questions, you were talking about, towards the beginning of your presentation, you were talking about your work as an industry product. So could you maybe talk more about the market demand of the applications of your research currently? And you're saying that product development cycle is anywhere from 12 to 20 years, so market demand in the future?
Well, you'd be surprised how many developers want to meet with me. There's a massive interest in it, and they see the relevance. So, and also practitioners. But when I mention like the hoops that one has to go through, this symposium that Naomi mentioned in the introduction that I co-chaired at MRS, which is the Materials Research Society. It's the largest annual conference for materials scientists. And we hosted this, one of the sessions, which was the first time that they had architects host a session. And it was cross-disciplinary, and we had some amazing work presented from scientists and architects, people like Joanna Eisenberg, and also architects like Skylar Tibbetts and so on. And it was amazing work, and the conversation that I did not anticipate to come out of that session, which happened over the course of 2 days, was around the people that we didn't invite that were actually super necessary. Lawyers, people who deal with code issues and ratings of materials. Some of the ratings that we're dealing with were produced in the 60s, right? And I'm talking about materials that are industry products out there in the market. Policymakers, right? Contractors, all of the people that are in industry that can make things happen. And so I would love to see more of that occur, whether it's through symposia or collaborative projects. I think in terms of my work, the probably the most promising project that potentially can move into an industry-ready product is coming from all of the textile work. So I am working on a permanent project in the Middle East that is allowing us to really push the boundaries of what's possible with knit and resilient materials. And that's where the practice is so relevant. I'm able to take topics and sometimes specific material systems and subject it to architecture and the constraints of making architecture. So, and I'm hopeful for the polybrick, but we need some more funding and more partners on that.
Well, I think on that note, I mean, your practice is really indicative of a next generation of practitioner of remodeling, really an entirely alternative mode of practice, which kind of has these interesting reciprocities between the teaching, the design studio, the lab, more conventional or traditional practice, which I would anticipate that in the next few years, a term you use that's ready to go outside. I presume that there's a lot that is ready to go outside, and that we'll see a lot of impact. So on behalf of NYIT, Dean Perbellini, Naomi, who coordinates the lectures, we'd like to thank you for joining us tonight, and please, let's thank Jenny for...
Well, thank you, Tom and Naomi and faculty, and especially the students. Thank you for your really thoughtful questions. I really appreciate them, and good luck this semester. As one of my mentors said to me, go forth and be useful.